Good morning everyone. So this is my next lecture based on information theory and coding in the subject obviously digital communication KEC 601. So in this topic we are going to see how the information theory is useful in case of digital communication, and there are various kind of coding techniques which is called as source coding techniques, that is Shannon and Huffman technique. We will discuss that also. So what is information? So any new knowledge about something is information. Whenever there is some uncertainty in a particular event, that is called as information. So messages containing knowledge of high probability of occurrence, not very informative. So this is very important term. So whenever there is high probability of occurrence, we will say that it is not very informative. But in the case of messages having very less probability of occurrence, have more informative. So a small change in the probability of certain output should not change the information delivered by that output by a large amount. So whenever there is some uncertainty, some minimum probability of occurrence of a particular event, it is called as more informative or more information. So we will connect this information with the probability itself. So whenever there is high probability, less information, less probability, high information. So basically information is inversely proportional to probability of occurrence of a particular event, we can say. So here we will define again the information. The amount of information of a symbol S with probability P is defined by this expression, which is 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 equivalent to log 2 1 upon P. So here P is the probability of occurrence of a particular event and IS is the information contained in particular message, and that will be defined as log 2 1 upon P. So I we can define as log 2 1 upon P here, or we can define log 1 upon P log base 10 1 upon P divided by log 2. You can define like this also. So here there are different properties of the information. That is, first one is the information content. Whenever the probability is 1, the information content is 0. A symbol that is certain to occur contains no information. The probability of occurrence lies between 0 and 1. So obviously the information content lies between 0 and infinity. The information measure is monotonic and it is non-negative. It's always be positive and in a increasing fashion. So we have P is equivalent to P1 into P2. So that's why the probability, the information content in a particular, in two events will be the sum of both the information content of the individual events. So IS is equivalent to IP1 plus IP2. So information is obviously additive for statistically independent events. So whenever there are independent events, we have the information will be the sum of both the individual information content contained in a particular messages. So we can see from an example, in communication log base 2 is commonly used, resulting in unit bit. For example, two symbols with equal probability P1 is equivalent to P2 is equivalent to 0.5. We have each symbol represent as IS is equivalent to, that is the information content in particular symbol, is log 2 1 upon P, that is log 2 1 upon 0.5. So that is equivalent to 1 bit of information. So we can define here the information IS is equivalent to log 2 1 upon P. So reminder, from logs of base 10 to log base of 2, we can change the log base 2 here with this formula, that is log x base 2 is equivalent to log x base 10 upon log 2, which is around 3.32 log x base 10. So now we will going to discuss about discrete memoryless source. Suppose we have an information source emitting a sequence of symbols from a finite alphabet. So if we have S which is emitting sequence of symbols S1, S2 and so on Sk. So here there are discrete memoryless source. The successive symbols are statistically independent. Assume that each symbol has a probability of occurrence Pk. So we will define the sum of all the probabilities of all the events is 1. So here we define that is summation over I is equivalent to 1 to k, Pk is equivalent to 1. So now we will define here source entropy. Entropy is another term related to information which is called as mutual information or the average information. So average information per message is called as entropy. So if symbol Sk has occurred, then by definition we have received information which is log 2 1 upon Pk or minus log 2 Pk. Bits of information. So the expected value or the mean value of this information is given by summation over k is equivalent to 1 to k pk I of sk, or it is written like this, that is summation over k is equivalent to 1 to k. With the help of minus sign we can also write, or we can write hm, which is entropy here of a source, is equivalent to summation over k is equivalent to 1 to k pk log to 1 upon pk. We can write like this also, we can write like this also, k is equivalent to 1 to k pk log to pk. Both these formulas are correct for the case of the entropy. So we can define here source entropy Hs, that is minus of summation over k is equivalent to 1k pk log to 1 pk. So its unit is bits per symbol or bits per message, you can say. So what is meaning of entropy? So what information about a source does its entropy give us? So it is the amount of uncertainty before we receive it. So it tells us how many bits of information per symbol we expect to get on the average. So there are source coding theory based on these information and entropy concepts. So what is the minimum number of bits that are required to transmit a particular symbol? So basically source coding technique is a compression technique. It is called as data compression technique. In various books you will find it. It is called as data compression technique. So basically data compression means minimum number of bits required to encode a particular message or a particular symbol. So what is the minimum number of bits that are required to transmit a particular symbol? How can we encode symbols so that we achieve or at least come arbitrarily close to this limit? So source encoding concerned with minimizing the actual number of source bits that are transmitted to user. How we will minimize these particular source bits into some lesser number of bits, we will see later on. So there is another concept which is called as channel encoding. So concerned with the introducing redundant bits to enable the receiver to detect and possibly correct errors that are introduced by the channel. So in the channel coding, we add some redundant bits at the transmitter side, and at the receiver side we will do some syndrome type of decoding methods, and then we will see how these decoding methods are useful for correction of the errors in a particular data which we are transmitting from the transmitter. So channel encoding is basically used for data error detection and correction, and the source coding is used for data compression, which is to make the symbols or encode the symbols with lesser number of bits. So next definition is here, average code word length. So IK is the number of bits used to encode the kth symbols, K the total number of symbols, PK the probability of occurrence of symbol K. So here we define the average code word length, that is capital L bar, that is summation over K is equivalent to 1 to K PK into LK. So LK is the number of bits which we will find with the help of the some coding techniques, that is either it will be a source or a Huffman or a Shannon-Fano coding technique. So with the help of these bits length multiplied with the probability of occurrence of these symbols, and then summing out all these symbols with the concept, we will find out average code word length. So it represents the average number of bits per symbol in the source alphabet. An idea to reduce average code word length, symbols that occur often should be encoded with shorter code words, and symbols that occur rarely will be encoded with longer code words. So obviously it will be defined with the help of the probability of occurrence. Whatever the probability of occurrence is high, the information content is low, and whenever the information content is low, lesser number of bits required to encode it. Similarly, if the probability of occurrence is less, more number of the content is very much informative, and more number of bits is required to encode a particular message or a symbol. So what is minimum code word length? What is the minimum code word length for a particular alphabet or source symbol? In a system with two symbols that are equally likely, if the probability of occurrence of the two symbols are equally likely, suppose it is 0.5, 0.5 or 1 by 2. Best one can do encode with each one bit only. So first one you can encode it with 0, and the second one you can encode it with 1. So whenever the high probability of occurrence, lesser number of bits, less information or lesser number of bits required. So it will be encoded with 0. Whenever there is less probability of occurrence, more information and more number of bits required. So it will be encoded with 1. So in a system with n symbols that are equally likely, probability of each symbols are equivalent to p is equivalent to 1 by n. So one needs L is equivalent to log to n or log to 1 upon p or log to p bits to represent these symbols. So we can have log 2 bits to represent these symbols, which is approximately equal to L is equivalent to log 2 n. So here if it is 8, suppose n is equivalent to 8. So we will have L is equivalent to 3. So 3 number of bits are required for each symbols to encode it. Next we have source coding theorem. So number of bits required to represent a typical sequence Sn is called as source coding theorem. And here we will define our average length Ln is equivalent to log to 1 upon Psn. And with this we will comes out to be a formula that is n into hs, or average length per symbol is for one symbol is given by L bar is equivalent to Ln upon capital N, which is equivalent to entropy of a source. So entropy is defined, we already defined the entropy, that is at bits per symbol. So given a discrete memoryless source of entropy hs, the average code word length for any source coding system is bounded with L is greater than equivalent to hs, or L bar is greater than equivalent to hs, where L bar is your average length for one symbol, which is equivalent to Ln upon capital N. So capital N is the number of bits required to encode a symbol, or Ln is the average number of bits, and average length will be defined with Ln upon n. So now we will come to first category of coding, which is called as Huffman coding. So how can one design an effective source coding algorithm? So we can use Huffman coding, which is also called as optimum coding method. So the Huffman coding is known as optimum coding. It yields the shortest average code word length. Basic idea to choose code word length so that more probable sequence have shorter code words. Whatever having the more probability of occurrence, lesser information, lesser code word is required there. Less probability of occurrence, more information and more code word length is required there. So Huffman code construction. Firstly, we have to sort the source symbols in order of decreasing probability. First step, take the last two smallest probabilities and assign each a different bit, that is 0 and 1, and then it will be summed and placed into a next column in a same way or a decreasing probability fashion. Repeat until one symbol remains only. So it's very easy to implement this algorithm in a microprocessor or a computer, and it will be used in JPEG or MP3. So we can see with the example here, we have list of symbols, that is S0 to S4, having probabilities of occurrence 0.4, 0.2, 0.2, 0.1, 0.1. So firstly, we will place the probabilities in decreasing order. Then we will sum the last two probabilities, that is obviously 0.1 plus 0.1, which is around 0.2, and then place this probability at the topmost in the same way, in the same fashion, decreasing order in the next column. So in the stage 2, we are placing here 0.4 to 0.4, but 0.2, obviously 0.2, 0.2 are similar to these, the sum also. So we will place at the topmost 0.2, and then this 0.2, and then this 0.2. Then again we will add the last two probabilities, that comes out to be 0.4, and that it will be placed at the topmost, then 0.4, then 0.2. Again we will sum 0.4 and plus 0.2, that is 0.6, and it will be placed at the topmost and the stage 4, and then we have left with only two probabilities. So whenever we left at the column, in the last column with two probabilities, we will stop there. Then we will assign the bits here, that is at the first, the upper part where you have summed is placed as 0, and the lower symbol or the probability is represented with 1. Similarly 0 and 1, 0 and 1, and 0 and 1. Then we will write the code words here. So S0, S1, S2, S3, S4 with probabilities, and with these code words we will see here, that is for 0.4 here to here, this to this, and that will be summed with this particular thing, and then it will be 0, 0. Similarly for 0.2, it will be 0.2 here, then this 0.2 here, then it will be 0, it will be summed here, then this 0.4 and that, and we will see that 1 and 0 is the code word for the 0.2. So we will write the code words in the back tracing obviously fashion, not in the front tracing fashion. You can read it from the front, but you write the code word in the back traced formula. Similarly, we can see for 0.1 here also. For 0.1 it is 0, then it will be summed, then here it is 1, and then it will be summed, here it is 0. So 0, 1 and 0 it is for 0.1, which is represented here. Similarly, for next 0.1 it is 0, 1, 1. So read diagram backwards for code words. It is written here. The average code word length we can find out with the probability, the bits. So here the bits are 2, 2, 2, 3, 3. So here the bits are this, and then this particular 2 is multiplied by 0.4, then 2 is multiplied by 0.2, then 2 is multiplied by 0.2. We will find out the average code word length, which comes out to be 2.2 bits per message or symbol. Then the entropy comes out to be 2.12. So for entropy, we will calculate here HS, summation over k is equivalent to 1 to, here there are 5 messages, pi or pk log 2 1 upon pk. With this formula, we can calculate the value of the entropy, which comes out to be 2.12 bits. So we will find out the efficiency and the redundancy of the code. Efficiency is defined as HS upon L and 2.12 upon whatever the length comes out to be. So whatever this value comes out to be, 97 or 96%, it will be the efficiency of the code. And there is another term which is called a redundancy. So this is efficiency, and another term is redundancy, which is gamma, and this is 1 minus eta. So gamma you can calculate with the help of the eta. Whatever the eta comes out to be, it will be calculated. It will be helped in the calculation of the redundancy here. Next, we have Shannon-Fano coding. So first, the messages are ranked in a table in descending order of probability. So obviously, in the same way, in the case of the Huffman coding, we have written the descending order of probabilities. In the same way, for Shannon-Fano coding, we define the probabilities in the descending order. The table is then progressively divided into subsections of probability near equal as possible. So we will divide with the table with some part that the sum of the upper part and the sum of the lower part will be equal or nearly equal. Binary 0 is attributed to the upper subsection and the binary 1 to the lower subsection. This process continues until it is impossible to divide any further. So the following steps shows the algorithm procedure of the Shannon-Fano coding. So these are steps. List the symbols in descending order of the probabilities. Firstly, divide the table into as near as possible into 2 equal halves of probability. Allocate binary 0 to the upper section and binary 1 to the lower section. Divide both the upper section and the lower section into again 2 parts. Until and unless you will get all the elements individually, you have to divide the table. Allocate binary 0 to the top half of each section and binary 1 to the lower half. Repeat step 4 and 5 until it is not possible to go any further. So you have to divide the upper and the lower half whenever you will until that time, whenever you will get the individual elements to be assigned a particular bits. So we can see from the example here, x1 to x8, these are the symbols, these are the probabilities, 0.25, 0.25, 0.15, 0.1, 0.1, 0.08, 0.06 and 0.01. So these are arranged obviously in the descending order. So firstly, we have to see from where we have to partition the probabilities in 2 equal halves. So if we sum both these probabilities, it will give you 0.5 and the below one is also 0.5 around. So we can easily divide from this place, from this point, and the upper half we assign the 0 and the lower half we assign the 1. Why we are assigning the upper half as 0? Because the probability is very high and the information is less, so lesser bit is required to encode it. So we assign the upper half obviously in every step, upper half as 0 and the lower half as 1. Again, we will break the element from here, upper half 0 and lower half 1. From here, we have this point, it is 0.25 and 0.25, the upper half is 0 and the lower half is all the ones. Again, we have this part, so it is 0.1 and it is 0.15. So we will split from here, it is 0 and it is 111, then 0.08, 0.07, 0 and 11, and then 0 and 1. So with this, we will finally comes out to be the coding part. 00 is the code for 0.25, 01 is the code for again 100, then 10. You have to read it horizontally and write all the codes. So we will again find out the L which is equivalent to L is equivalent to summation over K is equivalent to 1 to here 8 P K into LK, which is your length, and HM for HS is equivalent to summation over K is equivalent to 1 to K PK log 2 1 upon PK. With these formulas, you can calculate the HM and the average length, and then we will find out efficiency eta, which is HM upon L, which is comes out to be here 98.2%, and redundancy gamma, which is 1 minus eta. With these formulas, which we can calculate for both the Shannon and for the Huffman code, the values of the efficiency and the redundancy. So the last one is a channel coding theorem. So Shannon has given a channel coding theorem in 1948 for the calculation purpose of that, how the channel is responded to a particular bandwidth and a particular capacity. So he has given C is equivalent to log B log 2 1 plus S by N, this formula, where S by N is signal to noise ratio. So there will be a trade-off between the capacity of the channel and the bandwidth and the signal to noise ratio. So if the transmission rate R is very much less than C, then there exists a coding scheme such that the output of the source can be transmitted over a noisy channel with an arbitrary probability of error. So conversely, it is not possible to transmit messages without any error. So if R is greater than C. So important implication of this particular theorem is the basic limitation due to noise in a communication channel is not on the reliability of communication, but rather on the speed of the communication. So this Shannon has given this particular capacity formula, that is C is equivalent to B log 2 1 plus S by N. Suppose S by N is given in 10 Hertz, 10 dB, and bandwidth is given in 10 Hertz. We can easily find out the capacity of the channel. So thank you so much for this particular information theory part, which you have listened carefully, that how the information theory plays a very vital role in the communication, digital communication nowadays. We can define also here the channel coding schemes, which we have not defined here due to less time. So the first part is the source coding, which we have already discussed. That is the source Shannon and the Huffman coding, which is also called as data compression technique. So these techniques are useful for data compression, for placing all these symbols into a minimum number of bits. The channel coding techniques is another part of the information theory, and that is useful for error detection and correction, which is also very useful. So thank you so much. Have a nice day.